This video was produced by Virginia View, a consortium dedicated to promoting remote sensing outreach, education, and research through funding by the America View Consortium. This video was developed in partnership with the Virginia Geospatial Extension Program and GeoTED UAS. Its contents are solely the responsibility of the authors and do not necessarily represent the official views of America View, the USGS, or other partners. The mention of trade names or commercial products does not constitute their endorsement. Accuracy assessment compares a classified image to a reference image that matches the classified image with respect to scale, detail, categories, and projection. This is often conducted through a pixel-by-pixel comparison of a classified image to an image which is assumed to be a correct representation of the Earth's surface, such as an aerial photo. To determine how well a specific classification method performed, an accuracy assessment is conducted. Accuracy assessments are conducted for both unsupervised and supervised classifications and are always included in any report. In this chapter, we demonstrate how to perform an accuracy assessment by completing an error matrix, then calculating kappa. We will generate a set of random points, identify the informational class at that pixel, compile an error matrix, calculate the percent accuracies for each informational class and overall, and then calculate kappa. Begin with a new project and add the reclass of the unsupervised classified image created in Chapter 1 and the maximum likelihood classified image created in Chapter 24. Add the imagery base map option. Be sure to set the symbology to the correct informational class values and colors. To eliminate bias from an accuracy assessment, for example, only choosing pixels that are known to be classified correctly, a random points file is first generated. Go to the Analysis tab, Tools, and use the search word Accuracy. Choose Create Accuracy Assessment Points Spatial Analyst tool. For input raster, either of the classified images may be selected. This choice will limit the aerial extent within which the random points are generated and will automatically extract the class values when the new shapefile is created. We'll choose the unsupervised image. Name the Output Accuracy Assessment Points shapefile. The target field is classified. It's the name of the field within the reclass file that contains the informational class code. This was automatically populated when the reclass image was chosen. The number of random points defaults to 500. The number of random points chosen depends on the extent of the area, the number of informational classes, and other considerations. For our purposes, demonstrating an accuracy assessment process, we've reduced the number of random points to 100. 3 sampling strategies are available. We strictly want random choice, no stratification. Once the fields are populated, click Run. Change the symbology of the random points layer if needed to enhance their visibility, and open the attribute table. If all 4 classes are not present, you can simply generate another random sample and delete this one. Here you see classified values for each point were automatically extracted, and a second field called ground truth was added. This field can be used if the true value for each of your points is going to be based on field evaluation. We're not ground truthing, so we can just delete that field. Select the column and choose Delete Field. We want to add the values for the other classified rasters to this same random points accuracy assessment shapefile. Add a new field. I'll name it ML_class since we're adding the maximum likelihood supervised classification results to each point. Don't forget to save. Now we need to populate the ML class field. To add values from the supervised classified raster image to our point shapefile, we'll use the Extract Values to Points tool. Search for and open it in the geoprocessing window. Your input point features is the accuracy assessment points shapefile we just created. The input raster is the second classified image, in our case the maximum likelihood image, ML class. Name the output features. We'll call these Accuracy Assessment 2, then Run. Open the attribute table for this new point shape file, Accuracy Assessment 2. A new field is visible called raster value. This is the NLCD class value from the maximum likelihood classified image file. We need to calculate the information class value and populate it in the ML class field. This takes a couple of steps. First, verify which NLCD value belongs to each informational class. Just look at the symbology. Go to Map, Select by Attributes, and in the Select by Attribute geoprocessing window, make sure that the second Accuracy Assessment random point shapefile is populated under Input. Selection type should be New Selection. Under Expression, click on Add Clause. This is where we build the expression to select one of the NLCD classes. Select raster value for the field. Is equal to. Then from the drop-down arrow, choose one of the NLCD values. For this demonstration, let's choose 40 and run. All features with an NLCD value of 40 are highlighted. Remember from symbology 40 is forest, so we now need to change the ML informational class to 3 for forest. Highlight the ML class column and select Calculate Field. In the Calculate Field geoprocessing window, under ML class equal, type 3 and click Run. Now we see the ML class field for forest has updated to the informational class value. Do this for each of the 4 NLCD classes. We no longer need the raster value field, so it can be deleted. But we do need a field for the aerial imagery, which will be used to compare to our classified image. We'll be using the imagery available from Basemaps in ArcGIS Pro. This new aerial field must be populated individually. First, make sure the only image turned on is the basemap. Right-click on a row in the attribute table and select Zoom to. This zooms to the point, and we can clearly see that this is forest, which is associated with class 3. Go to the Edit tab, choose Attributes, and type 3 under Aerial. Continue this procedure until all 100 points are classified based on the aerial photo. And once all aerial points are assigned to a class, close the Attributes Edit window. With the attribute table open, right-click on the column for aerial and select Summarize. We're summarizing class values for aerial, so ensure aerial appears in the first statistics field. And we want a count of the number of pixels for each informational class. We're comparing to our unsupervised classified image, so it gets populated in the second statistics field, again with count as the statistic. Under case field, we want to list both again, aerial in the first blank, and then classified in the second. Select Run. This tool generates a standalone table and contents. If you right-click on the table and open it, we have a summary of aerial classes and unsupervised classes for all 100 points. Let's interpret the table. In this table in the first row is the number of points identified as urban in the aerial photo and also as urban in the unsupervised classification. For the second row, the number of points identified as urban in the aerial photo, but as agriculture in the unsupervised classification. In the fourth row, the number of points that are agriculture in the aerial photo and classified as agriculture in the unsupervised classification, and so on. Now we can compile the error matrix and calculate kappa. We're going to compile the matrix for the unsupervised classified image. From the tables we just looked at, the unsupervised image values were added to the random points file as classified. See your text for a complete explanation, but let's take just one row, the forest row. This is the number of random points that were classified as forest in the aerial photo but water in the unsupervised classified image. This is the number of random points that were classified as forest in the aerial photo but urban in the unsupervised classified image. This is the number of points that were classified as forest in the aerial photo and forest in the unsupervised classified image. This is the number of random points that were classified as forest in the aerial photo but agriculture in the unsupervised classified image. And this is the total of the row. So to calculate overall accuracy, which is the percentage of random points that are the same in both images for our matrix, that's 77 points. 0 for water, 8 for urban, 64 forest, and 5 for agriculture. And we have a total of 100 points, so our overall accuracy is 77%. CAPA provides us with insight into our classification scheme and whether or not we achieved results better than we would have achieved strictly by chance. The formula for CAPA is observed minus expected over 1 minus expected, and it takes several steps to compute it. See your text for details, but this is generally how it's explained. Starting with observed, observed is overall accuracy. Expected is calculated from the rows and columns totals. So to calculate what would be expected based on chance is the product matrix divided by the cumulative sum of the product matrix. The product matrix is the sum of the diagonals. The cumulative sum is the sum of all the cells in the product matrix. Using the CAPA formula, CAPA then is 0.525 or 52.5%. This means that the classification is 52.5% better than would have occurred strictly by chance. Remember, we only used 100 random points to conduct an accuracy assessment for this classification. In this example, the number of random points is very low. When conducting an accuracy assessment to support your research project, the number of random points should be much higher. We used a small number of values for the accuracy assessment simply to illustrate the process using a practical example. This concludes the chapter on accuracy assessment and the demonstration on remote sensing using ArcGIS Pro. As noted frequently within each chapter, the book serves as a guide to using ArcGIS Pro only. It does not provide sufficient information on making choices in remote sensing analysis specific to any individual project.